So good morning to all. Welcome to the second day of the free online class course on problem solving techniques in analysis presented by Day02 Academy. Today we are continuing the same analysis problems. Okay. Now we discuss the 26th problem today. Okay. So I think it is visible. Okay. So the problem says, suppose f is a function from R to R such that f of 0 equal to 0 and modulus of f dash of x is less than or equal to 5 for all x. We can conclude that f of 1. So what is the value of f of 1? Where it is lies. Okay, we have to use the mean value theorem. Okay, so 26th problem, they given that f is a function from R to R and then f of 0 equal to 0 and then modulus of f dash of x for all x is less than or equal to 5. Now we have to find out what is the value of f of 1. Okay, so therefore consider this interval closed interval 0 and 1. Now consider this function restricted to the domain closed interval 0, 1 to R. Now by mean value theorem, f of 1 minus f of 0 equal to 1 minus 0 into f dash of some c. Okay, so f of 0 is 0, therefore implies that f of 1 equal to 1 minus 0 is 1, that is f dash of c. But f dash of c is less than or equal to 5. That is modulus, if you take modulus, so therefore modulus of f of 1 equal to modulus of f dash of c, but modulus of f dash of c is less than or equal to 5. This implies that modulus of f of 1 is less than or equal to 5. Therefore, it lies in the interval f of 1 lies in the closed interval minus 5, comma plus 5. So this is the answer. Last one. So f of 1 is in the interval minus 5 to plus 5, closed interval. Now next problem. Let D be the subset of the real line. Consider the statement, every infinite sequence in D has a subsequence which is converges in D. So actually this is nothing but definition of sequentially compact. So what is the definition of sequentially compact? A set is said to be sequentially compact. If you take any infinite sequence in the set, it has a convergent subsequence. Okay, and then convergent point should be in the set D. So therefore this is nothing but sequentially compact. And we know that in the real line or metric space, sequentially compact implies compact. Both are equivalent. Therefore, look at this, which one is compact set? Compact means closed and bounded. But look at the first one, this is not bounded set. Therefore, this is not compact. Therefore, this is not sequentially compact. And look at the second one, it's a union of two closed set, therefore it's a closed. And then union of two bounded set is also bounded. Therefore, D is a closed and bounded, therefore compact. Therefore, it's a sequentially compact. But look at the third one, is not a closed set because one is not included in the set. Therefore, this is not closed. Therefore, this is not compact. Similarly, last one is not a closed set because this minus one is open. Therefore, again, this is not a closed set. Okay, therefore, this is very, very important consequence of compact set. You can say any infinite sequence in D as a convergent subsequence in D is sequentially compact, but then the metric space sequentially compact if and only if compact. Therefore, the second one is the correct answer. Okay. Now, look at the next problem. Okay. Again, f is a function from R to R, be a continuous function with f of 1 equal to 5 and f of 3 equal to 11. If g of x equal to 1, 2, 3, f of x plus t dt, then what is the value of g dash of 0? So again, we have to use the mean value theorem here. So 28th problem, again, f is a function from R to R. F of 1 is 5. F of 3 is 11. Suppose they define g of x equal to integral 1 to 3 f of x plus t dt. Then what is the value of g dash of 0? So what is the value of g dash of 0? So actually g dash of x is nothing but just f of the upper limit. What is the, because this is with respect to t, therefore you have to substitute the upper limit, lower limit for the values of t. Therefore this is nothing but x plus 3 minus f of x plus 1. So because we know the result, what is that? Integral a to b f dash of t into dt is nothing but f of b minus f of a. So instead of f here we have f dash, here we have f. Therefore, actually this we have to differentiate, right? So if you differentiate this, you get use the Leibniz formula. The differentiation goes inside. We get the partial derivative. Therefore, we get f dash. Okay. So actually, better we write one more step. What's the g dash? So after that, use the mean value theorem. So if you differentiate partially, so what is the okay, derivative? This is equal to integral 1 to 3 f dash of x plus t into dt. Others are 0. So we know that this is nothing but by mean value theorem. This is f of x plus 3 minus f of x plus 1. Now we know we have to find the value of g dash of 0. Therefore, substitute x equal to 0. We get f of 3 minus f of 1. So this is nothing but 11 minus 5 is nothing but 6. Therefore, g dash of 0 value is nothing but 6. So just you have to use the mean value theorem for the interval 1, 3. Closed interval 1, 3. Okay, next question. Look at this series. Suppose let f of x is nothing but value of the summation n equal to 1 to infinity sin nx by n square. Then what is the, now apply the limit x goes to 0. The what is the value of the limit x goes to 0 f of x. Now we have to use the Bayes-Assam test for this one. Suppose take actually f of x is nothing but the value of this series summation n sin nx by n square. Now call this is nothing but fn of x. So fn of x is nothing but the fractional n sin nx by n square. Now apply the modulus. Find what is the modulus of fn of x is nothing but modulus of sin of nx by n square. But sin is always bounded by 1. Therefore, this is less than or equal to 1 by n square. Since n is positive, therefore this is n square. Now we know that summation 1 by n square is convergent. Converges series implies that by Bayes-Assam test, summation fn of x converges uniformly. Converges uniformly. And they given that the value is nothing but f of x. Okay, so let f of x equal to the value of the summation fn of x. But actually, this series converges to the partial. What is the meaning of the summation value is f of x? The partial sequence converges to f of x. Now, what is the value of limit x goes to 0? F of x is nothing but limit x goes to 0. What is f of x? Summation sin nx by n square. Since this is uniformly convergent, therefore we can interchange this limit and this summation. Therefore, this is equal to summation n equal to 1 to infinity limit x goes to 0 sin nx by n square. Since this is n goes to infinity sin 0 0, therefore this converges to 0, therefore this value is 0. By using or you can use the sandwich lemma, you can show that the limit of this sequence is 0. Therefore f of x limit x goes to 0, f of x value is nothing but 0. Look at the first one, limit x goes to 0, f of x value is 0. Why? Because this is uniformly convergent, therefore we can interchange summation and limit. Therefore, just to take limit x goes to 0 to this term, we get 0. Therefore, limit x goes to 0, f of x is 0. Okay. Now, next problem. So again, let f comma g is a function of close to 0, 1 to r defined by f of x equal to x if x is of the form 1 by n and 0 otherwise, and g is a function defined to be for all the rational numbers in close to 0, 1, defined 1, for all other values 0. Okay. Now clearly, if you find the lower sum and upper sum or lower integral and upper integral for g, it is not Riemann integrable because the upper sum is always 1 and the lower sum is always 0. Therefore, lower integral is nothing but infimum of supremum of all the lower sum. Therefore, infimum supremum is always 0. Similarly, for g of x, therefore, it is not integrable. Now, so f of x is defined to be 1 by n if x is of the form 1 by n. 0 otherwise. So if you draw the graph of this function, so it is defined on close to 0, 1. For 1, it is going to 1. For 1 by 2, it is 1 by 2. So for 1 by 3, they define 1 by 3 and so on. For all 1 by n format, they define the identity function. Okay. So actually the defined is the x, right? So for all values of x in the close to 0, 1 is always 0. Therefore, it is discontinuous only at these points. Okay. Therefore, how many points we have? We have countably many points such that f is discontinuous. So f is discontinuous on the points this 1 by n. Such that n in n. Since it is countable, we know that if it is countable by discontinuous, if the function is Riemann integral. Okay, therefore f is Riemann integral. If a function is discontinuous at maximum countable number of points, the function is Riemann integral. So there is an important theorem. Therefore, this is Riemann integrable on the closed interval 0, 1. Now, if we look at the another function g, so g of x is defined to be 1 if x is in the rational numbers in closed interval 0, 1, 0 otherwise. So therefore, if we take any partition of the closed interval 0, 1, so 0, 1, if you take any partition, this is x0, this is x1, x2, x3, and so on. If you consider all the partition, so each interval contains both the rational and irrational, right? Therefore, the minimum infimum is always 0. Therefore, what is the maybe take p equal to this x0, x1, etc. xn is a partition. Therefore, what's the LP of f is nothing but lower value of this function. So lower value of the function is 0. Therefore, it's always 0. So what is u of f p comma f is upper sum. So this capital M is always 1. So therefore, we get a 1. Now, if we take a supremum of all LP of f over all the partition, if you take any partition, each interval contains 0. Each interval contains a rational number. Therefore, its corresponding value is 0. Therefore, for each partition, this is 0. Therefore, if it is supremum, that is also 0. So again, for if you take infimum for over all the partition over f, UP of f, that value is always 1. So this is nothing but lower integral. This is upper integral. Lower integral, upper integral exist, but not equal. Therefore, it's not integrable. So here they given function g. Okay. So called g. So therefore, g is not integrable. Not Riemann integrable or integrable. So it's not Riemann integrable. Therefore, look at the options. The first one says both are Riemann integrable. That is not false. That is not true. Why? Because g is not Riemann integrable. Look at the last one. They say both are not Riemann integrable, but we know that f is Riemann integrable because it is discontinuous at countable number of points. Therefore, it is Riemann integrable. Look at the third option. They say g is Riemann integrable, but we know that g is not Riemann integrable. Look at the second one. F is Riemann integrable. We know that, but g is Lebesgue integral. So, but you have to focus on this topic, Lebesgue integral. So you have to study something and measure theory. Okay. So anyway, you can easily say that this is the only options remaining, right? Because all the other options are not valid. So therefore, the B is the correct answer. Now look at this one. Sum of two sets. So suppose E1, E2 be two non-empty sets of a non-linear space X, and they defined the sum of two sets as X plus Y. So this is actually wrong, not in X. Okay. Okay, yeah, it is in the set, correct. Yeah, X plus Y in the X, where X in E1 and Y in E2. So which are the following statements are true. If E1, E2 are convex set, then what about E1 plus E2 is always convex. Why? So you can easily prove that sum of two convex set is convex. Okay. So how to prove this one? Suppose convex in what? If we take 1 minus t times some any point x, t into y belongs to the set A for all x comma y in A, and then this t varies from close to 0 comma 1, then we say is a convex set. Okay. So here E1, E2 is a convex set. Now we have to consider this Z, maybe Z1, t times Z2, where Z1 and Z2 belongs to E1 plus E2. Therefore, Z1 is of the form some x1 plus y1, Z2 is of the form x2 plus y2. Okay, where x1, x2 are in E1, y1, y2 is in E2. Therefore, this is nothing but 1 minus t into this is x1 plus y1 plus t times Z2 is nothing but x2 plus y2. Now simplify this and take x, this is x1, okay, plus t times x2, again plus 1 minus t into y1 plus t into y2. Since E1, E2 is a convex set, this is belongs to E1 and this is belongs to E2. Since sum is there, therefore this belongs to E1 plus E2. Therefore, E1 is convex, E2 is convex, then E1 plus E2 is also convex. Therefore, first one is correct. Okay. Actually, which of the following statement is false? The word is missing is false. Okay. Suppose if we take E1, E2 two open set, either E1 or E2 is open set, then sum is open set, because we can write sum as union of two open set, right? So E1 plus E2, so it can be written as, so everything is of the form x plus y, such that x comma x in E1 and y in E2. So this can be written as union of, if we fix one set and vary the another element, set of all x in E1, so x plus E2. So union of all these like x plus E2. So assume that E2 is open now. So now suppose E2 is open, you can easily show that x plus E2 is also open set. So you know this is clear. This is the nothing but arbitrary union of open set, because each x plus E2 is open. Therefore, this is arbitrary union. Therefore, arbitrary union of open set is open. Therefore, E1 plus E2 is open. So otherwise, suppose E1 is open means we can write this is all y belongs to E2, E1 plus y. So again, this is also open set. This arbitrary union again is a open set. Therefore, either E1 is open or E2 is open. The sum is always open. Therefore, that is also correct statement. But look at the last one. If E1 is closed and E2 is compact, then the E1 plus E2 is also closed set. So for here we have to use for compact, we have to use the sequentially compact. So closed means what? It contains all the limit points. Okay. Suppose they given that E1 is a closed set, E2 is a compact set. So we have to show that E1 plus E2 is closed set. Therefore, if we consider E1 plus E2, we have to show this is closed to that. It is enough to show that this closure is a subset of E1 plus E2. We have to prove this one. So therefore, if we take any point Z here, we have to show that Z is a limit point of E1 plus E2. That means we have to find a sequence in Z1, E1 plus E2, which is converges to Z. Okay. And then that Z should be in the set E1 plus E2. Suppose if we take Z belongs to E1 plus, but this containment is always true. E1 plus E2 is always contained in E1 plus E2 closure. So any set is contained, its closure. This is always true. Now we have to do the other implication, containment. Suppose if we take Z belongs to this, it implies that there is a sequence Zn in Z1, E1 plus E2 such that, okay, this is sequence in this such that Zn converges to Z. Now, therefore, Zn is a sequence in E1 plus E2. Therefore, Z is of the form Xn plus Yn, where Xn in E1 and Yn in E2. Since E2 is a compact set, therefore it is sequentially compact. Therefore, given any sequence, we can find a subsequence, maybe y and k in E2, such that this y and k converges. Maybe this converges point, maybe we call y. This y should be in the set E2 because it's a compact. Therefore, it's a sequentially compact. Therefore, for each corresponding the subsequence, we have a subsequence in xn. Again, we call the same x and k. So this is subsequence. Okay, in a subsequence of xn. Now, what is this x and k plus y and k? So we know that z, similarly for z and k actually is nothing but x and k plus y and k. This converges to, because zn converges to z, therefore all the subsequence also converges to the same point z. Okay. Now we know that y and k converges to y. Now subtract yn. Therefore, x and k. If you subtract y and k, so that is cancelled using the algebra limits. This is converges to z minus 1. Because y and k converges to y. Now subtract this, we get this one. Since this is a sequence in E1 and this is a limit, therefore E1 is in the set E1. E1 is a closed set, therefore this is a limit point of E1. E1 is a closed set, therefore this z minus y should be in the set E1. Because E1 is closed set, therefore it contains all the limit points. Therefore we call this element is x, z minus y equal to some element E1. Maybe we call x. Therefore z equal to x plus y. Since x is in E1, y is in E2, therefore z in E1 plus E2. Therefore, we take arbitrary element z in E1 plus E2. That element should be in the E1 plus E2. If we take closure, element in the closure, it should be in the set. Therefore, sum of closed and compact set is always closed set. But look at the third option. Suppose E1 plus E2 must be closed if E1 and E2 are closed set. It is not true. There are some standard examples there. So that is, if we consider sum of two closed set is need not be closed, but sum of two open set is always closed. Sorry, always open. Suppose E1, if we take E1 is set of all integers, so set of all integers is a closed set in R. And we know that if A is a closed set, if we take multiply some scalar, this is also closed set. If A is closed, then alpha times A is also closed. Since Z is a closed set, therefore we take Z2 is some root 2. Root is some scalar. Root 2 times Z is also closed set. Therefore, both E1 and E2 are closed set. Now, what is E1 plus E2? So, is of the form actually n plus root 2 times m, such that m comma n is in integers. So, actually, this is actually dense set. So, dense in R. So, dense set never closed. Okay. So, the proper dense set never closed set. If it is dense, that is not closed. Therefore, sum of two closed set is not closed. So, how to prove this is dense set? So, what is the definition for this? Given any real number x and y, with x less than y, we can always find elements E1 plus E2 in between x and y. So we can always find some m plus m root 2 in between x and y. Therefore, this set is the dense set. So this is standard proof. You can see in the Kumaresan sir book, Topology of Metric Space book. You can see the proof of this theorem. So they give the same exercise, same set Z1, Z and root 2 times Z. Therefore, sum of two closed set need not be closed set. Okay. Therefore, but they said it must be closed set. Therefore, this is a false. Now, next one. Suppose let f of x equal to minus 3 pi in the interval minus pi to x to 0, and then 3 pi if 0 less than x less than pi is the periodic function of period 2 pi. Because why period 2 pi? Because length is minus pi to pi. Therefore, period is 2 pi. What is the coefficient of sine 3x in the Fourier series expansion of f of x on the interval minus pi to pi? Okay, so therefore you should know the Fourier series expansion of given any function. So this is nothing but a0 by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx. So the summation is common for all an and bn. Now, so what is an? An is nothing but 1 by pi interval minus pi to pi f of x into cos nx into dx. So bn is nothing but 1 by pi interval minus pi to pi f of x into sine nx dx. So we have to find the values of sine, the coefficient of sine 3x. Therefore, find b3. So question is, so if substitute n equal to 3, we get sine b3 sine 3x, right? So the question is find the coefficient of sine 3x. Therefore, we got to find the value of b3. Therefore, now substitute n equal to 3. Therefore, we get b3 is nothing but 1 by pi. So integral minus pi to pi f of x into sine 3x into dx. Therefore, this is equal to 1 by pi. You can split this interval. Integral is nothing but minus pi to 0. In this interval, what is the value of this is nothing but minus 3 pi. Or minus pi to 0, the value of f of x is nothing but minus 3 pi. So therefore, this is minus 3 pi times sine 3x into dx plus interval 0 to pi. The value of f of x is nothing but 3 pi sine 3x dx. Now simplify this. So you can take pi outside and then cancel that pi. Therefore, minus 3 times integral minus pi to 0 sine 3x dx and plus 3 times integral 0 to pi, and this is sine 3x dx. Now this is equal to minus 3. If we integrate sine 3x, we get a minus cos 3x by 3 minus pi to 0 plus 3 times again if we integrate this minus cos 3x by 3 0 to pi. Now substitute the upper limit, lower limit, and then we can cancel this 3. 3 is common, therefore cancel. And then if we take minus outside, therefore minus minus plus, therefore cos 0 value is 1. Okay, minus if you take cos minus 3 pi, cos is a even function. If you cos of minus x same as cos x, therefore cos 3 pi is minus 1. Because cos n pi is nothing but minus 1 power n. Here n is nothing but 3. Therefore it's minus 1. Plus, again we can cancel this 3, and we have minus here. So therefore this is minus of, again cos 3 pi. So cos 3 pi value is minus 1 minus cos 0 is 1. So this is nothing but 1 minus minus plus, therefore 2 minus, again this is minus 1, this is minus 2. So therefore minus minus plus, therefore 4. So therefore the coefficient of sine 3x is 4. Okay, therefore the answer is lies between 3.99 and 4.01. Therefore the correct exact answer is 4.00. That is 4. Now next question. So which are the following statements about the little LP and big LP? So little LP is nothing but set up all sequence such that summation mod s. So just state what is small LP and big LP. So small LP space is nothing but set of all sequences such that the summation of modulus of xn power p. This series is convergent series. Finite means converges. So collection of all sequences that the corresponding series converges, then we collect the sequence, that is LP. And big LP is nothing but set of all functions f such that integral modulus of f of x power p whole power 1 by p, or sometimes just take modulus of p, modulus of f power p dx. Okay, this dx is less than infinity, finite. So this LP. So what's the condition on? So and then there is a condition on p and q. So 1 by p plus 1 by q equal to 1. Okay. Suppose if 1 less than or equal to p, less than or equal less than strictly less than q, less than infinity. Suppose p is smaller, then this LP is preserving the same inequality. Therefore, now look at this one. 3 is less than 7. Therefore, the small L power 3 is always contained in L power 7. But the big L is a reverse process. Now, 6 is less than 9, but we have a reverse containment. So L power 9 is containment. So big LP reverse containment, but small. So this small LP is subset of small LQ, provided P is less than Q. So again, P is less than Q. The big LQ is contained in big LP. It's a reverse containment. Okay, so this is important properties of small LP and big LP. So therefore, you can easily say that This is the correct answer. All others are false. Okay. So again, look at this. This actually the same thing. I did some mistake here. The options. Okay, I think somewhere is missing. Something missing here. Okay. Anyway, idea is nothing but just this. If you big LP is reverse containment, and small LP is the same containment. Now next question. Which of the following is not a metric space on X? So you can easily show that the second one is not a matrix, and these are all metrics. Why is a maximum is not a metric? It's not satisfy the second condition. What is the second condition on metric space? Suppose the distance of x comma y equal to 0 if and only if x equal to 0. Okay. Suppose they define maximum of either d1 comma 2. So maximum therefore is always bigger than 2. Therefore is never 0. Okay, maximum of this is never 0. Therefore, does not satisfy the condition d. Maybe we call capital D of x comma y is defined to be maximum of distance between x comma y or d1 of x comma y comma 2. So suppose equal to 0. Suppose d of x comma y equal to 0. We got to show that x equal to y. But if it is 0, it is not possible, right? Otherwise, we take the same x. What is the distance between x comma x? So we know that if x equal to y, then distance between x comma y should be 0. But this is nothing but maximum of d1 of x comma 2. But anyway, d1 is a metric. Therefore, distance between x comma x is 0. Therefore, maximum of 0 comma 2. What is the maximum of 0 comma 2 is 2. Therefore, here distance between x comma x is not equal to 0. Therefore, this is not a metric space. This is not a metric. So therefore, the maximum is not metric, but minimum can be minimum is a metric space. And then this is also metric. This is average of metric. Therefore, this is also metric. We can easily show. The second one is not a metric. It's not satisfy the second condition. Okay, next question. Complex analysis. Suppose f is a function from C to C is an entire function with f of 0 is 1 and f1 of 1 equal to 2 and f dash of 0 equal to 0. Suppose if there is m such that f double dash of z is less than or equal to m, then what is the value of f of 2? F of 0 is 1, f of 1 is 2 and f dash of 0 equal to 0. Question. F is a function from entire complex number to complex number is an entire function. Then they given f of 0 equal to 1, then f of 1 equal to 2, then f dash of 0 equal to 0, and then there is m such that modulus of f double dash of z is less than or equal to m. Okay, so these are all hypotheses. Now we have to find the values of f of 2. So first you got to write what is the f of z. Since f is an entire function, therefore it is differentiable at all the points of z. So f is entire, therefore f dash is entire, f double dash is also entire. Okay. So now this is derivative is bounded. Therefore, since f dash is an entire function, f double dash is an entire function, and this is bounded by Liouville's theorem, this f double dash should be constant. So maybe we call that constant is some C1. Now we integrate both the side, we get f dash of z this side, and this is C1 times z from again some other integrating constant, maybe we call C2. So again we have to integrate, we get f of z, and this is nothing but C1 z square by 2 plus C2 z plus some other constant C3. Now we have to find the value C1, C2, C3. So we know that they given that f of 0 equal to 1 and f of 1 equal to 2 and f dash of 0 equal to 0. Now look at this, maybe we call the first equation or second equation. In the first equation substitute z equal to 0, we get f dash of 0. So this is equal to f dash of 0 is nothing but 0. Now substitute z equal to 0, we get C2. So therefore C2 should be 0. Now substitute the second equation z equal to 0, we get so 1 equal to f of 0. So if we substitute z equal to 0, we get C3. Therefore C3 should be 1. Now substitute f of 1. So f of 1 is nothing but 2. Now substitute z equal to 1 in the second equation. So therefore C1 by 2. Because z square is 1. And then we know that C2 is always 0. and then plus C3 is 1. Therefore, now simplify this. This 1 and 2, 1 cancel. Therefore, 1 equal to C1 by 2. Now cross multiply, we get C1 equal to 2. Therefore, C1 equal to 2, C2 equal to 0, and then C3 equal to 1. Now substitute all the values in the second equation. We get f of z. So therefore, f of z equal to C1 is 2. Therefore, these 2 and these 2 cancel. Therefore, we get just z square. And then C2 is 0. Therefore, C3 is 1. So this is our f of z. Now, what is f of 2? Question is, what is the value of f of 2? Therefore, 2 square plus 1 is nothing but 5. Therefore, the value of f of 2 is 5. Now, next question. So, in the Lorentz series expansion of the function f of z equal to 1 by z into z minus 1 valid for mod z minus 1 greater than 1. What is the coefficient of the term 1 by 1 minus z? Okay. Now, we have to write this function in some other form. Okay, 1 by z into z minus 1. 36th problem. So they give f of z equal to 1 by z into z minus 1. So we can rewrite this as, so 1 by z minus 1 whole square divided by 1 plus 1 by z minus 1. Why? Because it just simplify, you'll get this one. So what is the, keep the numerator. So if you simplify the denominator, you get z minus 1 plus z by 1 by z minus 1. Now this 1 cancel, we get and this 1 z minus 1 z minus 1 cancel. Therefore 1 by z into z minus 1. So that is same thing the given function. Therefore the given function can be written as the form 1 by z minus 1 whole square by 1 by this one. Actually this is nothing but you can keep this z minus 1 whole square into 1 by 1 plus 1 by z minus 1. Okay. Now, since they given that mod z minus 1 is bigger than 1, therefore just to cross multiply, we get 1 by mod z minus 1 is always less than 1. So maybe we call this number is x. Okay. Therefore now substitute 1 by z minus x value is x. Therefore we get a 1 by. Let us keep this one. This look like 1 by 1 plus x. Okay. So 1 by 1 plus x. So we know that this is geometry series converges. What is the value of this geometry series converges to 1 minus x, right? So that is 1 plus x square plus etc. This converges to 1 by 1 minus x provided mod x is less than 1. So here x is nothing but mod this one. This is always less than 1. Therefore, this is nothing but the value of this series. So here we can write, but we need a minus x, right? Here 1 minus x format. Therefore, we can write this minus of minus x. Okay. Therefore, we can write here. So this is nothing but 1 by 1 minus of minus 1 by z minus 1. So therefore, this is nothing but 1 by z minus 1 whole square. So this is nothing but summation this x power n, where n equal to 0 to infinity. So this is nothing but 1 by z minus 1 whole square summation n equal to 0 to infinity. If you take minus outside, therefore minus 1 power n 1 by z minus 1 power n. Now just to multiply this is 1 by z minus 1 square inside. So we get summation n equal to 0 to infinity minus 1 power n by z minus 1 power n plus 2. So now question is, what is the coefficient of 1 by z minus 1? Okay. So we get, so substitute n equal to 0. So we get 1 by z minus 1 square. So the starting term is minus z minus 1 whole power. If you substitute n equal to minus 1, substitute n equal to minus 1, then only we can get the term 1 by z minus 1. But here n varies from minus 0 to infinity. Therefore, there is no term. There is no term 1 by z minus 1. Therefore, the coefficient of 1 by z minus 1 is 0. Because in the Lorentz series expansion, and f of x does not contain the term 1 by z minus 1. Therefore, it is the coefficient of z minus 1 by z minus 1 is 0. Okay. Now, next question. Suppose x and y are matrix spaces. If we suppose f is a function of x to y is a continuous function. F is a continuous function, and we know that continuous image of compact set is compact, continuous image of connected set is connected, and so on, right? But if S is open, then f of f is open is in general is not true. Okay. So if it is f is a open map, then if S is open, then f of s is open, provided f is a open map. But this is not a continuous function in or be a open map. Okay. Therefore, the first one is false. But the second one says if S is connected, then f of s is connected. Yeah, it is true because continuous functions takes to connected set to connected set. Therefore, that is true. And then look at the third one. If S is closed, then f of s is closed. Again, this is not true. When this is true, if assume f is a closed map, then this is true. But this in general, this is not a closed map. Therefore, again, that is not true. So again, f is bounded, then f of s is bounded. Again, this is not true. Okay. So if we take s equal to open in the 0, 1, the function defined to be 1 by x. So the f of s is unbounded. Okay. So we can give so many functions. Okay. So another example is take s equal to open in the 0, 1. So the function f of x equal to 1 by x defined on this set. So therefore, what is f of s? Is nothing but unbounded, because if substitute 1 by n, we get n. What is just 1 by n value? Because 1 by is in the interval close to open at 0, 1. What is f of 1 n? So this is unbound. Therefore, if s is bounded, if s is acted as continuous function, maybe it's an unbounded set. Okay. So therefore, the second one is the correct answer. Now 38 question. Suppose I equal to close to 0, open 3. And j be the set of all rational numbers in the interval close to 4, 6, and k be the Cantor set, and let L equal to 7 plus x. Then what is the Lebesgue measure of the set I union j union L is equal to? Okay. So now we have 3 set. So one is I is nothing but close to interval 2, open 3. And then j is nothing but set of all rational numbers in 4, 6. Set of all rational numbers in the interval close to 4, 6. And k is nothing but Cantor set. And then using the Cantor set k, they define L. So L is nothing but x plus k, where x is any element in R, I think so. So x in k, okay. 7 plus x. So 7 plus x. So L equal to 7 plus x, where x in Cantor set. So actually this is nothing but 7 plus capital K. So this is a definition. Now, what is the question is, what is the value of I, what is the measure of I union j union L? So look at this one, everything is a disjoint set. So if you draw the graph, so 0, 1, and then 2, 3, and then 4, maybe we can take here 6, maybe this is 5. Okay. Now Cantor set k. So Cantor set we can get from close to 0, 1. Therefore, k should be here inside the close to 0, 1. So I is nothing but 2, 3. So I is here, and j is nothing but set of all rationals in 4, 6. Therefore, j should be here. So what about L? So L is nothing but just you got to add 7 to the each element in k. So k in 0, 1. Therefore, L should be 7, 8. Because you got to add 7 to the each element. Therefore, you can get L should be in the 7, 8. Okay. Therefore, this I, J, L. So everything is a disjoint sets. Okay. So there is no common element. Therefore, measure of this union I union J union L is nothing but measure of each set. Measure of I plus measure of J plus measure of L. So measure of I is nothing but length of the interval. This is 2, 3. Therefore, length is 1. Plus J. What is J? rational numbers in 4, 6. So settable rational number countable set, right? So we know that the measure of the countable set is always 0. Therefore, this is 0. Why the measure of j is 0? J is a countable set. Measure of the countable set is 0. Therefore, that is 0. Now, what is the measure of L? So we know that there is a theorem. Measure of A is same as measure of x plus C. If you add any element x, the measure of A same as measure of x plus A. So therefore, measure of L x plus or 7 plus k. This is nothing but L, right? So this is another measure of k. So we know that measure of the Cantor set is 0. So this Cantor measure of the Cantor set is 0. So therefore, total the measure is 1. Just to use the property that measure of the union is nothing but sum of the measure, because it's disjoint sets. The measure of A equal to measure of x plus A, and then measure of the Cantor set is 0. So using the three property, we get the answer is 1. Okay, next. So we already discussed this rational directional derivative of the function in the direction this at the point this one. Therefore, just you have to partial derivative with respect to x, y, z, and then you have to take the dot product with this direction. After that, you have to substitute the value. So x square 2y 4z square. So for 39. So u of x comma y comma z equal to x square minus 2y plus 4z square in the direction equal to 3 by 5 I vector. So 3 by 5, 4 by 5 k minus 4 by 5 k. There is no j vector. Okay, at the point 5 comma 1 comma 0. 5 1 0. Yes, right. Now you got to find ux dot. What is ux? So you need to find ux. So what is the partial derivative with respect to x is x. So uy is nothing but minus 2, and then u is equal to 8z. Now you have to take the dot product with this direction. So ux nothing but 2x times what is the coefficient of I? 3 by 5. Here the coefficient of j, there is no j, therefore uy into 0, because there is no j vector, plus 8z into minus 4 by 5. So after that you have to substitute 5 1 0. So now substitute x equal to 5. If substitute x equal to 5, this 5 and 5 cancel, therefore 2 into 3 is 6, plus anyway this term is 0, minus if you substitute z equal to 0, therefore this term is 0. Therefore we get 6. So the direction derivative of the function u, the direction this, at the point this is 6. Okay, now this one, let un equal to n factorial by 1 into 3 into 5 into 2n minus 1. Then what is the limit of this sequence? Okay, so again we know that one result, that is limit n goes to infinity modulus of un plus 1 by un. If this is less than 1, then the limit is 0. The limit of un is 0. Limit n goes to infinity, un is 0. So therefore you have to find this one. So here what is our un? Un is nothing but n factorial by 1 into 3 into 5, only odd terms, 2n minus 1. Therefore n factorial. So you have to multiply and divide it by the missed term. So what is the missing term? 2, 4, 6, etc. 2n. You have to multiply and then divide by the missing term. Therefore we get in the numerator denominator 1 into 3 into 4 into etc. 2n minus 1 into 2n. Okay, because we have to multiply 2, 4, 6, 2n, and then we have to divide 2, 4, 6. Therefore the denominator we get 2n factorial. The numerator we get n factorial. And then in the numerator, each term contains 2. Therefore, you can take 2 outside. So how many terms we have? We have n terms. Therefore, we can take 2 each term. Therefore, we get 2 power n. And the remaining is 1, 2, 3, etc. This. And then this is nothing but n factorial. And divided by this is 2n factorial. So the action is nothing but n factorial whole square power n by 2n factorial. So this is nothing but un. Now find un plus 1 by un. So this is nothing but if substitute n equal to 1, therefore n plus 1 factorial whole square 2 power n plus 1 by 2n plus 1 factorial. And then un, therefore again n factorial square times 2 power n. In the denominator we get a 2n factorial. So now we can cancel. So again this 2 power n and then 1 2 power n cancel. We have 2 here. So again this n plus 1 factorial we can write n plus 1 into n factorial. Therefore this is square is there. Therefore n square into n factorial square. And then this is 2. And the remaining this is 2n factorial by this is if you multiply 2 inside, therefore 2n plus 2 factorial. This is n factorial square. Now we can cancel this n factorial square. Okay. Now what is 2n factorial? So 2n factorial, 2n plus 2 factorial is nothing but product of first 1 into 2 into etc. So the last term is 2n plus 2. What is the previous term? 2n plus 1, because we have to subtract 1. So again, what is the previous term? 2n. Therefore, you can take this is 2n factorial. Therefore, this is nothing but 2n factorial times remaining term 2n plus 1 into 2n plus 2. Okay. Therefore, this is equal to n plus 1 square 2 into 2n factorial by this 2n plus 2 factorial can be written as 2n factorial times 2n plus 1 into 2n plus 2. So this 2n factorial cancel. You can take 2 from this term and then this 2 and this 2 cancel. Therefore, this is equal to n plus 1 square into 2 by 2n. You can take 2n plus 1 into, if you take 2 outside, therefore n plus 1 into 2. Therefore, these 2 cancel. So again, you can take 2 n outside. Again, you can take n outside from here. Therefore, if we take n outside from the numerator, we get n square times 1 plus 1 by n square. Again, if you take n from this term, the way 2, if we take 2n outside from this term, therefore 1 plus 1 by 2n. If you take n from the second term, therefore we get 1 more n, therefore n square into 1 plus 1 by n. Okay, now n square cancel. Now as n goes to infinity, this goes to 1 and this goes to 1, this goes to 1. Therefore, totally this goes to 1 by 2. 1 by 2 is less than 1. Therefore, the limit value is less than 1. Therefore, limit n goes to infinity, un value is 0. Okay. So the value of the sequence is 0. Okay. Now, next question. So what is the residue of the function f of z equal to e power z by z square into z square plus 9 at the point z equal to 0. So z equal to 0 is a pole of order 2. 2 is the order of the pole. Okay. Now we have to find. So what is our f of z? F of z is equal to e power z by z square into z square plus 9. So along at the point z equal to 0, what is the residue? So here residue is pole 2, order 2. Therefore, residue of f of z. So at the point is 0. 0 is okay at the point 0. So here m. So we know that here m equal to 2 because order is 2. Pole of order 2. Therefore, 1 by limit. First, what is the formula? Limit z goes to 0. 1 by m minus 1 factorial. M minus 1 is 1 factorial. This is 1. Therefore, and then d by d z. M minus 1. Therefore, m minus 1 is 1. Okay. And then z minus 0 whole square into f of z. So this is equal to limit z goes to 0. D by d z of z square into f of z. What is f of z? E power z by z square into z square plus 9. Therefore, we can cancel z square. Therefore, we get limit z goes to 0. D by d z of e power z by z square plus 9. Now you differentiate this u by v method. Therefore, limit z goes to 0. Z square plus 9 whole square and then you can keep this z square plus 9, and then differentiate e power z, we get e power z minus keep e power z, and then differentiate z square plus 9, we get 2z. Okay. Now substitute z equal to 0. So if substitute z equal to 0, e power 0 is 1, and this is 0. Therefore, we get in the first term 9 minus, if you set z equal to 0, we get 0 here. Divided by substitute z equal to 0, you get 9 square. Okay. Therefore, 9 square 9 cancel. Therefore, we get 1 by 9. Okay. So answer is 1 by 9. Residue. So next 42. Pick out the false statement. So suppose the first one is, we know that sin z is an entire function. Suppose this is true. This says that sin z bounded. We know that bounded entire function is constant, but sin z is not a constant function. Therefore, this is not valid. Okay. Now look at the second one. We know that in the real case, sin square x plus cos square is equal to 1. But what about the complex case? Sin square z plus cos square equal to 1. Is this true? Yeah, this is true. Why? Is the identity theorem or uniqueness theorem. So the theorem says, suppose there are two analytic functions. Okay, so this is question number 42. So the uniqueness theorem. The uniqueness theorem says, suppose two entire function or analytic function, not entire function, two analytic function f and g. Suppose we collect all the z such that f of z equal to g of z. Okay, maybe we call s. So s equal to set of all z. The condition that f of z equal to g of z. Suppose this s as a limit point in the domain. Suppose f and g defined on some domain D. Suppose s as a limit point in D. Then f of z equal to g of z for all z in D. Okay. Now we have what is our f of z in this case? Sin square z plus cos square z. Take g of z equal to 1. So we know that again s equal to set of all z such that sin square z plus cos square z equal to 1. We collect all the real satisfying this condition. So we know that a real number is always contained. Therefore, R is a subset of the set S, because all the real numbers satisfying this condition, x square, sin square x plus cos square x equal to 1. Now R is there are infinitely many limit point is there for R. Therefore, everything is in the domain. Therefore, this S as a limit point. Therefore, this is true for all Z in the domain. Therefore, this is true. So sin square x plus cos square z is 1. This is true for all z. This is always true statement, because this is true for real case by uniqueness theorem. This is true for complex case. Similarly, for the third one, we know that sin 3x equal to 3 sin x minus 4 sin cube x for the real case. Again, by using identity theorem, this equation is true also for a complex number. Therefore, these two are true statements always. The question is what are the false statement? The first one is false statement. Okay, because we know that in the real case, sin x is bounded by 1. Okay, but the identity theorem says only for the equality, not for inequality. Okay, but here we have inequality. Therefore, identity theorem or uniqueness theorem holds only for equality. Okay, therefore the first one is the false statement, and this is contrary to the Liouville's theorem. Now next, so this 43 says, which of the following function is analytic in the entire complex plane? So this is f of x comma y. Otherwise, we can write f of z. We can write this is e power iy, right? E power minus iy, because this cos y plus I sin y. Therefore, the first option can be rewrite as given that f of x comma y equal to e power x times cos y minus I sin y. We can rewrite this as f of z equal to e power x. This is e power minus I. Therefore, this is e power x minus I. So we know that z equal to x plus iy. Therefore, this is e power minus z, e power z. So we know that whenever f is analytic, the partial derivative of f with respect to z bar should be 0. But here, if you take what is dou f by dou z bar, again is e power z bar. It's not equal to 0. Therefore, this is not analytic function. So your function is analytic So this is complex form of a CR equation. So dou f by dou z bar should be 0, but in the first case, this is a function of z bar. Therefore, it's not analytic. If it is function of x bar, therefore look at the last one. So actually, this is f of z equal to, this is actually z bar. So f of z equal to z bar. If you differentiate with respect to z bar, we get to 1. Therefore, this is not equal to 0. Therefore, this again is not an analytic function. So this can be written as, this is e power minus x and this e power minus I. Therefore, the second one is e power minus x minus iy. So this is e power minus z. So we know that e power f of z is analytic. Whenever f is analytic, then so minus f is a polynomial, minus z is a polynomial. Therefore, e power minus z is a analytic function. Therefore, the second option is always analytic. Look at the third one. The third one says f of z equal to minimum of 2 comma x square plus y square. So minimum of 2 comma x square plus y square. So this is our f of z. So minimum of these two always less than or equal to 2 as well as less than or equal to x square by 2. Anyway, just this is less than or equal to 2. So suppose you see, and because the question is analytic on complex number. So entire. So the question is the entire complex plane. Suppose f of is entire, since this is bounded by 2. Therefore, this entire function is bounded. Therefore, should be constant. But f of is not constant function. So therefore, that is not an entire function. Therefore, second is the correct answer. Now look at this one, 44, and pick out the true statement. So suppose there is an analytic function f on C. So whole complex number, if it is possible, there is an analytic function satisfy the condition f of 2i equal to 0 and f of 0 equal to I and modulus of f of z less than or equal to 2. So this is bounded and there is a entire analytic on C is nothing but entire function. So is it bounded? Suppose there is an entire function, it is bounded, therefore should be constant. The constant means what? All the values maps to single value, but this 2i maps to a different value 0 and then this 0 maps to some other value. Therefore, this is not constant. Therefore, such a function does not exist. Similarly, look at the second option. There is an analytic function f in the open disk this such that f of 1 by 2 equal to 1 and f of 1 by 2 power n equal to 0 for all integers. Now again use the now collect use identity theorem. Fourth problem. The second option. Suppose you collect S is nothing but set of all z such that f of z equal to 0. So they given that f of 1 by 2 power n is 0 for all n greater than or equal to. Therefore, this collection is always contained in S. So this S contains always 2 power n such that n greater than or equal to. So this has a limit point. This converges 0, right? Therefore, it has a limit point. Therefore, by uniqueness theorem, f of z equal to 0 for all z in the unit disk. Okay. But they given that f of 1 by 2 is 1. But in the this 1 by 2 should be in the unit disk. But we know that everything goes to 0. But they given that f of 1 by 2 equal to 1 in this case. Therefore, there is no such a function exist. Now, similarly, look at the third option. There is an analytic function f on C whose real part is given by x square plus y square. It is not possible. Suppose such a function exists means this function satisfies the Laplace equation. So what is the uxx is 2, uyy is 2, again 2 plus 2 is 4. Therefore, it's not equal to 0. Therefore, this u does not satisfy the harmonic, that is Laplace equation. Therefore, it is harmonic. Therefore, there is not such a function exists. So if it is analytic, then both the real and imaginary parts satisfy the Laplace equation. But this u not satisfy the Laplace equation. Therefore, this is not true. Therefore, none of these above is the true statement. Next question. If I plus 1 plus I power 9 by 1 minus I power 7 equal to P plus IQ, then what is the value of this P? So 1 plus I power 9 by 1 minus I power 7. So maybe we call this P plus IQ, then what is the real part of this? So take Z equal to 1 plus I. Okay, therefore this is Z power 9. Actually, this is nothing but Z bar. Okay, what is Z bar? 1 minus I. Therefore, this is power 7. Therefore, we can write Z by Z bar power 7 into Z square. We can just write split the 9 into 7 plus 2. Okay. So now find what is Z by Z bar first. So what is z plus z bar? 1 plus I by 1 minus I. Now multiply 1 plus I both sides, numerator and denominator. In the numerator, we get 1 plus I whole square by, this is a plus a minus b, a square plus b square, we get 2. Therefore, if you expand this 1 square minus 2ab plus b square, b is I, therefore I square is minus 1. Therefore, this one cancel, and this is minus 2a, and divided by 2. Therefore, 2 to cancel, we get minus I. Okay, therefore, this value is nothing but minus I power 7. Now, what is z square? Again, we just know what is z is nothing but 1 plus I square. Therefore, this is minus I power 7. If you expand this I square, a square minus 2ab plus b square. So again, this one cancel, this is 2. Therefore, finally we get a minus, if you take minus 1 outside, therefore minus 1 power 7 into I power 7. And this is, we have a minus 2I. Minus 2 into I. Okay. So therefore, you can merge this I, and then this minus into minus. This is odd power, therefore this is minus 1. And this we have minus 2, therefore we have 2 into I power 8. And we know that I power 4 is 1. Therefore, I power 8 is 1. Therefore, this should be 2. Therefore, there is no imaginary part. Therefore, p value equal to 2. Okay. P value is 2. So similarly, you already studied this one, how to find the residue of this one. Okay, they're asking a residue of 2. So if we take z outside, we get z into z minus 2. So therefore, 2 is a pole of order 1. Therefore, so maybe we quickly, what is f of z? So f of z equal to z plus 1 by z square minus 2z equal to z plus 1 by, if we take z outside, therefore we get z minus 2. Therefore, z equal to 2 is a pole of order 1. Therefore, what is the residue of f of z at the point 2 is nothing but, here pole is 1, therefore limit z goes to 2. 1 by m minus, m is 1 here. So because pole of order 1, 1 minus 1 by m minus 1 factorial, 0 factorial. Therefore, again, the d power m minus 1 derivative. Therefore, there is no derivative. Therefore, directly I can write z plus 1, because we have to z minus 2 into f of z. F of z is nothing but 1 by this 2. So this term cancel. Now again, substitute z equal to 2, equal to 3 by 2. So 3 by 2 is the answer. Our next question. So again, let f is a function of C to C be analytic, write z equal to x plus iv and f equal to u plus iv. Then which of the following is false statement? So this is always true statement, because it's a complex form of CR equation. Derivative is equal to ux plus ivx. So this is correct. And then it is analytic, therefore real part uxs plus uiv equal to 0, because the real part is always satisfied the Laplace equation. Therefore, this is true statement. But look at the third one. This is f double derivative. This is cube, right? Therefore, in the formula says, in general, the Cauchy integral formula says f nth derivative of z naught equal to n factorial by 2 pi I integral over the comma f of z dz by z minus z naught power n plus 1. Therefore, in this they say the option given that second derivative of 0. Therefore, should be here 2 factorial. 2 factorial by 2 pi I over f of z by, they give a z cube. So that is n equal to 3. Therefore, the 2 factorial is missing in the third option. Okay. Therefore, this is a false statement. Now, this look at the 48th. Suppose u equal to x into y is a harmonic function. So, what is a harmonic conjugate? Is satisfy the Laplace, that is a CR equation. If you differentiate this with respect to x, we get y. Therefore, this is the vx. So maybe look at the last one. Maybe you get, this is a harmonic conjugate of this. Okay. Now, next question. So just apply the CR equation. Find the v. So what is the possible values of v is the last one. So next, the 49th question is, suppose a function is conformal at a point z naught, the definition is derivative is not equal to 0. So if the derivative is at the point is not equal to 0, then the function is conformal mapping at the point z naught. Direct definition. Okay. So the derivative at the point is not 0, then we say f is conformal at the point. Now the last question. suppose z equal to 1 plus I by I minus 2, then what is the real part of z? So you can easily check and then multiply and divided by f of z be 1 plus I by I minus 2. Multiply and divide by I plus 2 by I plus 2. So therefore this is 1 plus I into I plus 2 or by this is a plus I into a minus ib. You take minus out from the first term. This is a plus ib into a minus ib. Therefore a square plus b square. And the numerator we get 1 into I 1 into 2 plus I into I minus 1 plus 2i by minus 5. Therefore we get this is 3i. The numerator 3i minus 1 by minus 5. Right? So therefore what is the real part? 1 by 5. Sorry, this is plus 1. Yes, this is 2 minus 1, therefore plus 1. Therefore what is the real part of this one is minus 1 by 5. Minus 1 by 5 is the real part because this minus is common for both the real part and imaginary part, right? So therefore minus 1 by 5 is the real part of this z. Or okay, okay, thank you.